Hey, it's Jim, and this is level 1 of the CFA program, the topic on quantitative methods and the learning module on hypothesis testing. You probably have noted that this is a relatively long learning module, and you might think that there are lots and lots of LOSs, but let me just show you that there are only 3. And the first 2 explain hypothesis testing and construct hypothesis test. Those 2 LOSs make up the bulk. I mean, probably 95% of this learning module. In fact, we only have just 1 or 2 slides on parametric and non-parametric tests. But I warn you that this is, in the 50s of slides in this slide deck. It's a long learning module. And I know over the years that level 1 candidates have difficulty with this particular topic. And some of them even say something like, well, you know what? How many questions on level 1 exam can this be? Maybe 4, maybe 5. I'll just go ahead and guess. Maybe I'll get 2 of them right, and there we go. It doesn't hurt me too bad. Well, let me just warn you, as a good old college professor, and trying to help you pass not just level 1, but level 2 and level 3, is that you will see these LOSs in level 2, especially when we get into multiple regressions and we do time series. And even in level 3, there's a series of LOSs on type 1 and type 2 errors. So here's my advice, is let's go ahead, put on our working gloves, put on our boots, let's get the shovel out, and let's pay attention over the next, 50 or 60 minutes or so, and get to work. Our goal is not only to master these LOSs, but our goal is to retain them inside of our brain so that we are on the path to success. So let's start with that first one. Explain hypothesis testing. Now, I want to warn you, you should know this by now, that at the end of every one of these slide decks, I always ask you to go to the questions at the end of the learning module. There are 20 at the end of this one, and 19 of them sound like they could have been extracted from an undergraduate statistics exam. So what I'm going to do during this recording is I'm going to try to use some real-life examples to help you ask statistical questions. I'm not convinced that the CFA Institute will just limit its testing in the questions at the end of the learning module, but I'm guessing that they're going to litter it with some of the questions similar to what we have inside of this slide deck. All right, so look at this thing here at the very top, an assumptive statement about a problem idea or some other characteristic of a population, and that could mean almost anything. I could come up with a statement about a problem or idea or some characteristic of the population of James Bond movies. I could say, you know what, Sean Connery is by far the superior James Bond, and we could have a conversation about this. However, in the statistics world, it's no longer sufficient to be able to just have an argument about which James Bond is superior. We need data to back up our assumptive statement. And then we need to run some tests on that data to be able to make a statistical claim. And you'll see what I mean as we go through some of these examples. I'm going to go ahead and give you 2 quick examples here. Let's suppose that you are the general manager of an NBA team, and you're thinking of signing LeBron James to a contract when his contract with his current team runs out at the end of this year. And let's suppose that you believe that you can evaluate LeBron James's contribution to your team based on just his points per game. Now, what you could do is you could go to LeBron James's, what has he been playing, 20 years or so, and you could look at every game out there. Now, even though NBA statistics are readily available, let's suppose that they're not, and you had to go and watch every game and collect all of his points. Well, that takes too long, right? 20 years, 82 NBA games, however many playoff games. You'd be here forever collecting that. So you're probably going to collect a sample. So let's just suppose you randomly collect a sample of 100 LeBron James games, and you plot those on a horizontal axis. 19, 25, 45, 61. I think LeBron had 60 points in a game. All right. So what are we going to do with that data? Well, we're going to go back to an assumptive statement. Our assumptive statement is something like, we think LeBron can help us win an NBA championship. Okay. Well, here's the data to support it. Now, the institute is probably not going to ask you about LeBron James on the exam, but it might say something like, hey, let's suppose that we're a portfolio manager and we're looking at the difference between dividend-paying stocks and non-dividend paying stocks. We think that dividend-paying stocks are going to outperform. So what could we do? I mean, we could get in our car and drive to the floor of the New York Stock Exchange, and we could collect data on dividend-paying stocks and non-dividend-paying stocks all the way back to 1792 when the New York Stock Exchange began its trading. Well, of course, that's just way too much time and energy and resources, so we'll take a sample. And let's suppose that we get a sample of 100 dividend-paying firms. And we take a look at their stock returns during the course of some time period, maybe it's a year, and we plot those along a horizontal axis. Now, you know this from our previous learning modules. There are two parameters that we're really interested in based on those two distributions, LeBron James's point distribution and the dividend-paying firm stock return distribution, the mean and the standard deviation. And those two parameters are going to be super important as we go through this, this slide deck. All right, so look at the bottom teardrop there. Hypothesis testing involves the collection and examination of a representative sample. All right, this is what I just said, right? LeBron, dividend-paying firms. Now, here's a great exam question. And at the end of this learning module, there are a couple of these that say something like, hey, which of the following is an important next step in the process of hypothesis testing? So we have 6 of these. We're going to state the hypothesis, figure out what's the appropriate test statistic, and we'll go ahead and look at a handful of them inside of this slide deck. But these are test statistics that are going to be important throughout levels 1 and 2 and 3. So remember these things. We're going to do a t-test. We're going to do a z-test. We're going to do a chi-square test. We're going to do an F test. So select the appropriate test statistic. This is one great question at the end of this learning module. The Institute gives you a sentence or two and says, which one is the appropriate test statistic? Is it T? Is it Z? Is it chi-square? Or is it the F test? Specify the level of significance. Of course, I'm guessing that you're aware of this from previous learning modules, is that the common level of significance, we want to do maybe a 95% confidence level, maybe 99% confidence level. So we have to pick this, but it's almost certain that the Institute would say, hey, let's do this at 5%, let's do this at 1%. State the decision rule regarding the hypothesis, which includes looking back at the hypothesis. And we'll do null and alternative hypothesis here in a second. And then we need to figure out what our decision is going to be. Is LeBron James worth signing? Is it worth investing in a dividend-paying stock? Then we'll have to do some calculations, and then we'll have to make a decision by looking some number up on a table, whether it's the T, the Z, the chi-square, or the F table. So let's go through these in just a little bit more detail. And I'm going to try to get through these fairly quickly because I think I summarized them on that previous slide. All right, so state the hypothesis. We need to figure out what the null hypothesis is. And the Institute is very clear on this, and stats books tell you this all the time. The current state of the knowledge about the population parameter, that is the subject of the test. And so these tests can be either two-tailed, and I'll talk a little bit more about that in a second. So that's the blue box on the left, where we have an equal sign, or they can be one-tailed, where we have a greater than or equal to, or less than or equal to. I mean, we could have the null hypothesis that LeBron James and Steph Curry would add the same value to our team, or that would be the left blue box. Or we could say, hey, Steph Curry would add more value than LeBron James. There's the less than or equal to, or just the other way. Now, what you want to do is you want to set up the null hypothesis so that if your If your assumptive statement is true, then you reject the null hypothesis. So we say something like, hey, dividend-paying firms, are exactly the same as non-dividend paying firms, right? So that would be a two-tailed test. We want to reject that because our assumptive statement is that dividend paying firms have a greater annual return, or however we want to say it. And by the way, just because I picked dividend paying firms, or you could go the other way. I mean, if you thought that non-dividend paying firms had higher growth potential than dividend paying firms, then you could just flip that. Now, this is right out of a stats textbook, and here's one of the questions at the end of this learning module. Here is the formal presentation. So there's HO, which is the null hypothesis, and there's the three of them going down, versus the alternative hypothesis. And sometimes it's noted as HA for alternative, sometimes it's noted as H1 for alternative, and it would just be the opposite of whatever the null hypothesis is. That should make sense. All right, so what did I say earlier? We could have a one-tail or a two-tail test, and if we have a selected significance level, maybe 5%, look at the bottom there, we have an alpha of 5%, what we need to do is worry about the difference between our sample mean and what we think the population mean might be, and in accord with the relative standard deviations. Now, what we can do is we're going to probably standardize this normal distribution, and I'll show you that here in just a second. So here, stating the hypothesis that we have case 1, case 2. Let me go to case 3 here real quick. Whoops, I went too far. I want to do this because most tests are two-tailed. So there's our null hypothesis in the blue, that mu, the population mean, is equal to some number. And that number could be, what is LeBron's score? 30 points a game. What's the rate of return on a dividend yielding stock over the course of a year? You know, maybe it's 5% or 10% or 15%, versus the versus the alternative hypothesis, which is a not equal sign there. So that's your key. If there's a not equal sign in the alternative hypothesis, then it has to be a two-tailed test. So there's our picture of the normal distribution down at the bottom. And so what we're saying is that the alternative is that the mu is not equal to x, meaning that it could be way to the left or it could be way to the right. So we have what's called this critical region in the light shaded blue down there on the bottom right and the bottom left. Now, this is important. If we have a 5% significance level, what we need to do is cut that 5% in half and put 2.5% on the left tail and 2.5% on the right tail. And we have a good example later on in this slide deck. Now, let me go back to the previous slide. If you have a one-tailed test, case 1 or case 2, you can say something like, hey, we're going to go and worry about to the left, which means you throw the entire 5% in that left-handed tail, or you can throw it all to the right. We don't have a picture here, but you can envision a picture down at the bottom right where the entire 5% is thrown in the bottom right. So one tail test, you got 5% all the way to the left or to the right. Two tail test, you have 2.5 and 2.5 in each tail. All right, selecting the appropriate test statistic. We'll do this in several examples here, but there's a good green boxed formula for you. All we're going to do is we're going to say any kind of a test statistic is really the difference between the sample statistic, like the mean, and the hypothesized value. Let me go back to the LeBron example. I could say something like, look, if we sign LeBron, we think with our offense, he's going to score 40 points a game. Well, if we go back and look at his random sample, what did I say, 100, and he averaged 30 points a game in his 20-year, inside of those 100 sample games over his 20-year career, well, the numerator would be 30 minus 40, right? The hypothesized value. And then what we do, and we always do this, we're going to divide by some kind of a standard deviation. Here it is, the standard error of the sample statistic. We're going to use that test statistic here. Let me go back here. In this two-tailed test, that test statistic is going to fall somewhere on that horizontal line. If it falls in between the two lightly blue shaded areas, then we fail to reject the null hypothesis. If it falls all the way out to the right or left, then we reject the null hypothesis. And that's the way the test statistic works. Now, here we go. You'll recall that sometimes I asked you to get out your phone, take a picture. So go ahead, take a picture of this slide. You might as well work on your memorization skills right now. You'll need to have all of those test statistic formulas memorized. You might as well do it now because you'll have to repeat this in levels 2 and in levels 3. Notice that, what is that, the third column there. There's the t, there's the chi-square, there's an f, and then there's another t, and then there's another chi-square. You might say to yourself, wait a minute, Jim, didn't we do a z distribution? And here's my summary of the difference between the t and the z. Do not tell your stats professors that I told you about this. If your sample size is 30 or less, go ahead and use the t. Some people might even say less than 30, but let's not split hairs. If it's greater than 30, then use the z, because the t distribution, it normalizes into a regular old standardized normal z distribution at higher sample sizes. And so t for small samples, z for large samples. Don't tell your stats professor, but you can't go wrong if you remember that. All right, how about continuing our conversation about selecting this appropriate test statistic? What about a type 1 and a type 2 error? So let me go ahead and read the statistics interpretation and definition. You ready? Type 1 error occurs when we reject a true null hypothesis. A type 2 error is the failure to reject a false null hypothesis. Boy, that sounds like it's right out of a stats textbook. And you might ask yourself the question, okay, Jim, I'm waiting for you to tell me what that means. Now, interestingly enough, or coincidentally enough, I have just recently made a level 3 video in which the Institute is asking the level 3 candidates to distinguish between type 1 and type 2 errors. What did I say at the beginning of this recording? You're going to have to know this stuff all the way throughout the program. Here's even more evidence. So here's the example that we talked about in that level 3 recording. Let's suppose you're a pension fund manager and you manage, several $1 billion worth of assets. And let's face it, that's just too much, right? You can't do this all by yourself. So you decide to hire an external portfolio manager. So what do you want to do? Well, let's just suppose you need just one person. So you hire 5 individuals, right? Really smart men and women. They come to you and you interview them. And what do you want to do? You want to pick the best of those 5. So what are you going to do? You can make 2 errors in your decision. You can either hire a manager that's going to underperform, which would be a type 1 error, or you could fail to hire a portfolio manager that is going to outperform. Now, the cool thing about all this, which means it's challenging, is that when you make that decision, you don't know if you've made a type 1 or a type 2 error. Only after you see the performance of your portfolio manager that you hired and the performance of the 4 that you didn't hire will you know whether you have made a type 1 or a type 2 error. So I think it's really cool if you remember it this way. Type 1 is when you hire a stinky portfolio manager. Type 2 error is when you fail to hire an awesome portfolio manager. If you remember those 2 examples, then those 2 sentences, they leap off the page and you say, oh yeah, that makes perfect sense. Type 1 error, we reject a true null hypothesis. Type 2, we reject a false null hypothesis. All right, quickly through this, back to the level of significance. This is the alpha. So what we're going to do is we're just going to pick. It's typically 95%, could be 99%. I mean, it could be 50%. What we'll see is that, boy, if you pick an alpha of 50%, then you're really not putting too much emphasis, too much confidence inside of your data collection. I mean, at 50%, I mean, you could say 20%. I mean, you could even say 0%. You could say, I want to make this decision with a 0 probability of making a type 1 error. So that's the alpha. That should make perfect sense. Here's a good camera. Get your camera out, take a picture of this. This is in probably every statistics textbook that you've ever seen. So there's a good 2x2 table of when a type 2 error and when a type 1 error is occurred. Those are in the red boxes. Notice that you make the correct decision in the green boxes. Now, the power of the test is related to the selection of your confidence level back here. Well, let me go back to, this is your level of significance or your confidence level. This is alpha. We call this beta, right? Statisticians, they're very clever, right? Alpha and beta, first two letters of the Greek alphabet. But remember that this power of the test, this is a good exam question, is going to be, look at that bottom box down there, 1 minus beta. So this is the probability of making a type 2 error. So there we go, alpha, type 1, beta, type 2. And I think that you should easily be able to remember those. Those are the likely questions on the exam. Let me go ahead and just caution you. You don't want to say something like alpha is 5%, therefore beta is 95%. That's not true. Now, the reading doesn't teach you how to compute the power of the test, which turns out to be 1 minus beta, this power of the test. What you have to do is you have to draw, here, let me go back here just really quickly. I'm going to go way back here. What you have to do is draw two of these normal distributions, sample and population, or two samples, or just two of these things, and you have to overlap them. And the beta of it is some small slice in there. And there's a really cool statistics way of calculating, where am I here? Calculating this probability of a type 2 error, but it's beyond. And in fact, in my 20 years or so, I don't think the Institute has ever asked us to calculate the power of the test, and they don't do it here. So, all right, what's the decision rule? So going back to my comments a few slides ago, where I said if that test statistic falls inside of those two light blue shaded areas, then we fail to reject. Now here our picture is just of a one-tailed test. So notice what we have on that left-hand side. We have the critical region. All right, so compare that to the non-critical region. So if our test statistic falls to the left of the critical value that we're going to get from the table, and I'll show you how to do that here in just a minute, then we go ahead and reject the null hypothesis. So to the left, here's a one-tailed test. To the left means that we reject. To the right means that we fail to reject. So there we go. Let me go back here. There's the critical region on the one tail. There's the critical region on another one tail, but in the opposite direction. And there's what I was talking about earlier. In that previous slide, we had light blue. Now we have light red shaded. Now, one of the quickest ways to go ahead and make this decision is to compute the p-value, which is, here, let me go back here. Let me go to, let's go to the bottom table here. So if we compute the p-value, so what do we have if our significance is 5%? We have 2.5 on the left and 2.5 on the right. If our test statistic falls to the left of that, it'll have a p-value of less than half of 5%. And I'll show you that here in just a second. So look at the bottom block point, the smallest level of significance at which a null hypothesis can be rejected. Now we can do this for one-tailed tests. So there's the first two blocks, and then the two-tailed test, you sum those probabilities. This is what I was just saying a second ago. But it's probably really important for us to go ahead and work through a problem. Are you ready for this? So 50 CFA charter holders, average IQ of 105. Previous studies show that IQs are normally distributed with a standard deviation of approximately 20. All right, so at 5%, is the mean IQ of CFA charter holders greater than 100? All right, so let's go back. I'm not going to swing back. Let's go back to that table, right? I asked you to take a picture of that table. Here's our test statistic there, right? Well, there's the null hypothesis, so that our mean is 100, and our alternative there is denoted as H1, so the mu is greater than 100, so this is a one-tailed test, right? So there we go. We have 105 minus 100 in the numerator. So let me go ahead and give you just a simple example. Do you remember back in kindergarten when your kindergarten teacher put on one table 105 apples and put on another table 100 apples, and they said to you, to the class, hey, are there the same amount of apples on each table? And you counted them and you counted them and you were like, no, they're not. There's 105 and there's 100. So mathematically, there's a difference that we learned back in kindergarten. But now the mathematical difference has to be tested to determine whether it has statistical significance. So statistically, it's possible that 105 equals 100. And we use this test statistic there. So we do 105 minus 100 in the numerator. So that's 5. So your kindergarten instinct says, wait a minute, 105 is not the same as 100. Therefore, the answer to the question is yes, CFA charter holders have higher IQs. Yes, that's obvious. But we have to divide it by standard deviations adjusted for the sample size. Oh my gosh, you ready for this? This is such a cool thing. So remember the difference between mathematical differences, which the Institute is not going to test us on, but the statistical difference. So we have to ask ourselves the question, is 105 minus 100, is that statistically significant? We know it's mathematically consistent. So what we're going to do is use the normal distribution. It's 50, so we're going to use Z. Let me just remind myself, did I say T when I first came on this slide? I can't remember. I'm not going to rewind. I may have said T, so let me correct myself if I did. So there's Z. So what we're going to do is we are going to get out our Z table. There's the Z table. And by the way, if you need the Z table, the Institute will give you this. They probably won't give you the entire table. They'll give you, an abbreviated version of the table so that you have to, well, what are we going to do? We're going to run our fingers down to 1.7. So what was our number back here? 1.768. Now, the Z tables, they only go out to 2 decimals, so we're going to have to round. So we go down to 1.7, and then we add 0.7, so 1.77, right? And there's the intersection. What do we get? 96. Subtract that from 1, and we get 384, which is less than 5%, 3.84%. So we have sufficient evidence to reject the null hypothesis. So what was our null hypothesis? That the CFA charter holders have the same IQ as everybody else out there. So we reject it, right? Our 177 falls in that middle, in that left range. No, where would it be? It would be in the right range, right? So over in the bottom right, it's over in that critical region. So we say, CFA charter holders have a statistically significant higher IQ. Now, let me just pause. In a different learning module, we're going to have extensive conversations about the code of ethics and professional standards, and the Institute always asks us to be very careful. We cannot tell anybody that just because we hold the CFA charter that we're smarter than everybody else. Now, statistically, that might be true, and this is just a made-up example, of course. It might be true, but then again, it might not be true. All right, how about moving on to tests concerning a single mean? What we need to do is we need to divide this into 2 different kinds of ideas. So go back to we did LeBron a couple times, so let's go back to my dividend-paying firms. So we collect this sample of dividend-paying firms. Now, it's just a sample, right? What did I say, 100? Well, how many dividend-paying firms have there been since 1792? I don't know, maybe 1 billion. Probably not 1 billion, but lots and lots. So sometimes we know what the population variance is. Now, I'm going to say this. We rarely know it, but sometimes we do. So if the population variance is known, well, then we use the Z. There's the equation right there, which is the same thing that we just used in that previous example. But notice in the denominator, there's a numerator in the denominator, right? There's that little sigma. That is a known population standard deviation, right? It's not squared. It's the square root of the variance. Now, we do the same kinds of things. So this is pretty much a repetitive slide, but there's the Z statistic. Notice that we have 1.96 positive, 1.96 negative to the left and to the right. This is pretty much a standard number that you should remember, 5%. Now, my econometrics professor when I was in graduate school, he said, look, you guys know the number is 196. I know the number is 196. But when you are just casually looking at some output, and we ran tons of regressions when I was in graduate school, he goes, just remember 2. So 1.96 is very close to 2. And so that was just kind of the thing that stayed with us in our brains. But the Institute will probably ask you to look up that number 196 on the table. All right, so what are we doing if the population variance is unknown? Well, then we're going to use a t. So here's a great exam question. Let me go back here. You ready? If the population variance is known, use z. If the population variance is unknown, use t. But then we need to bring in this concept of degrees of freedom. And notice we have n-1 degrees of freedom. Let me give you Jim's quick idea about degrees of freedom. Let's suppose you take one of my exams. Let's suppose you take 2 of my exams and you make the mean on the 2 exams is a 20. You know that on the first exam, you made a 10. You know the mean, but you don't remember. You can't remember what you made on the second exam. Well, you took 2 tests. You have n-1 degrees of freedom, 2 minus 1. If you know 1, what did I say, a 10, and you know the mean, it was a 20, then you know your performance on the second exam had to have been a 30. And that's really what degrees of freedom might be here. You probably don't ever have to know that for a CFA exam. But there we go. It's the same formula that we had. Here, let me go back. It's the same formula here, right? However, what are we substituting? Look, there's an S in the denominator. That S is the sample standard deviation. So we're going to use t with n-1 degrees of freedom. So let's go ahead and work through an example here. We're evaluating a balanced fund. Let's see, existence for 36 months. It has a mean monthly return 1.2%, standard deviation of 2.8%. According to a widely accepted financial model, this mutual fund was expected to have earned 0.9% monthly return. Okay, 5% level of significance, right? So are the actual results consistent with what that underlying expectation was? Now, if we were back in kindergarten, we would say 1.2 is not the same as 0.9. There's a mathematical difference. But now that we're a lot older than in kindergarten, we need to determine whether this is statistically significant. So let's run through our steps, state the hypothesis that the mean is 0.9, and then it's a two-tailed test because it could be either higher or lower. We're going to go ahead and identify the appropriate test statistic. It's going to be t because, what did we say? The standard deviation of monthly returns is 2.8%. So we probably don't know what that population is. So that population standard deviation is. So we're going to use the sample there in the denominator. 5%, that was given. So here in that last table, I showed you how to use the p-value. Here we're going to use the t-tables. So we're going to run our finger down, degrees of freedom, 36 months, n-1 is 35. Run our finger over to 35, and then run our finger over. Now here's where you have to be super careful on the exam, right? What was the level of significance? We were told it was 5%. So you might be tempted to run your finger down the 0.05 and come up with a 1.6, right? But wait a minute, it's a two-tailed test. So you have to chop the 5 in half, throw 2.5% on the left, 2.5% on the right. So there's our critical value of 2.03. All right, so let's calculate the test statistic. There's 643. So where does that falls? Here, we don't have a, hold on a second. We don't have a Here we go, right? That what was that number? 0.6 something. So that falls in the middle there, the white region. It's not outside of the shaded region, which was, what was that, 2.0 something, right? Remember 2. So the 0.6 is in the middle, so we fail to reject. So let's go back here. So what are we saying here? We're saying that we're failing to reject that null hypothesis because it's within that boundary, the white boundary that I was saying earlier. Let's go ahead and move on to a different question. What did I say to you at the very beginning? These LOSs, they take up 90% of our time, those first two LOSs. So remember what I said to you maybe 20 minutes ago, 30 minutes ago? Suppose we want to compare LeBron James and Steph Curry. Suppose we want to compare dividend-paying firms and non-dividend paying firms. All right, so the difference between the mean, right? LeBron may average 30 points a game, Steph Curry may average 25 points a game, or whatever that number is, right? Dividend-paying stocks may average 8% annual return. Non-dividend paying stocks, they may average 9% annual return. So there's a mathematical difference between those two means, but is there a statistical difference between those two means? So what we need to do is we need to do the same thing that we've done all up to this point, but then we need to add an extra sample, right? So that's why we have sample 1 and sample 2 down at the bottom. Now here's a slide. This is going to just make your eyes cross here, but this comes right out of the reading and it's right out of all statistic textbooks. So what can you do? You can say something like, hey, there's no difference between LeBron James' points and Steph Curry's points. So you would say mean 1 minus mean 2 equals 0. There's the two-tailed test, the null hypothesis in the blue, the light blue box at the top. But then you could say, wait a minute, I think LeBron is going to score more points than Steph. Or you could say, I think Steph is going to score more points than LeBron. And so you can do the green and the dark blue down at the bottom. Now, what does that test statistic look like? Well, it's going to be a t-test. But now we have n minus 1 degrees of freedom for sample 1 and n minus 1 degrees of freedom for sample 2. So what does that mean? You have n plus n, so we'll note that as n1 plus n2, right? And then minus 1 and minus 1, so you have minus 2. So there you go. Degrees of freedom, when you're comparing the difference between two means, has to be, and sample size 1, maybe you get 100 of LeBron's points, sample size 2, maybe you get 100 of Steph Curry, but maybe you have 200, or maybe you have 82, or whatever that number is, and then you subtract 1 and then subtract another 1. So there is the test statistic, and notice that in the blue box, we show you that SP in the denominator, that's kind of like the pooled standard deviation. You're really just kind of taking a weighted average of the two. Zeta Global Income Index, want to test whether returns are different for two distinct time periods, time period 1 and time period 2. So there's a mean, there's a standard deviation, sample size is the same number of days. Yeah, so 5% level of significance is 0.2%, the same as 0.15%. Well, kindergarten tells us no, but here CFA Program asks us to prove it. We need to prove it using some statistical test. All right, so there's the hypothesis that period 1 equals period 2. The null then is that they don't equal. So there is our appropriate test statistic again. There's our 5% alpha. So we'll go ahead and look at the T table. So notice, oh my gosh, what do we have? We have, well, what's 250 plus 250 minus 1 minus, well, that's 498. So this is what I was saying to you earlier about this kind of rounding. The T distribution, it becomes the Z distribution at super high sample sizes, greater than 30, essentially, but when it's infinity, see infinity down there bottom, that's 1.96. All right, so there's our There's our kind of pooled standard deviation, and then there's our t-value. So that falls inside of that white region. So we once again fail to reject the null hypothesis. So what are we saying? We're saying that, let me just go back here, period 1, even though it's mathematically different, it's not statistically different. Now, how about if we refine this conversation to go with dependent samples? So what we need to do is some kind of a paired data test, right? The difference between means of two different populations. All right, so look at just some examples down there in the green and the blue and the dark blue. You know, what we can do pre-dividend, post-dividend, we can collect samples, well, here, say 7 days before, 7 days after. And so that's one time period back there. That's another time period. So, you know, the stock is trading pre-dividend and post-dividend. Those are probably different kinds of samples. So what you can do is you can do this paired difference test. What I'm going to ask you to do is go ahead and pause the recording right now and read through these kinds of things and read through all of the boxes and see if it makes perfect sense to you. If it doesn't, I promise it will once we go through this example. There's our test statistic. Notice we have a D bar there. Those of you who are now coming back after looking at those boxes and having your eyes crossed there for just a second, let's do a quick and simple example. This really simplifies what this thing back here, boy, oh man, that sounds like it. That sounds like you're deriving the Black-Scholes-Merton option pricing model. I just made that up. All right, you ready? So we're evaluating the performance of BCD high growth index and BCD investment grade index. Oh my gosh, so what does that sound like? That sounds like equity securities. That sounds like fixed income securities, right? 2,050 days for both indexes. So there we have mean returns. There we have standard deviation of returns. Let's determine whether the difference is not zero. All right, so there's our null hypothesis. There's the alternative, two-tailed test. There's our t-stat. I showed you that in a previous slide. There's 5%. Let's go ahead, run our fingers all the way down. Right, 2,000. That's close to infinity. So there we have, oh my gosh, it's the same 1.96. Hello, McFly. Maybe my econometrics professor in college was right saying, just remember 2. All right, so here we go. You ready? This is how easy this is going to be on the exam. What were there, 5 or 6 blocks in that previous slide where I told you to pause. Look, the Institute is very likely to give you the 0022 down at the bottom right, and then the 3321, that difference in those standard deviations. And there it is, t of a minus 0.30. And so that's within the bounds. So once again, we're failing to reject that there is a difference. So we're saying that mathematically those two might be different, but statistically they are the same. All right, let's go ahead and continue moving onward, and let's go ahead and ask ourselves the question, what happens to a test of the difference between variances? What have we been doing so far? We have just been counting the number of apples in our kindergarten table. But there are really cool tests that say something like, all right, we count the number of apples on the table, but what about the difference between the two standard deviations? Wow. Hypothesis test concerning a single variance. All right, now I'm going to ask you to remember what we did in a previous learning module. Remember when we did returns and we said something like, monthly stock returns, they probably follow a normal distribution, or at least a nearly normal distribution. But what about stock prices? And remember when we made the assumption to continuous compounding, we said that, wait a minute, continuous compounded returns, they follow a normal distribution, but the prices that are used to determine those continuously compounded returns, they follow a log normal distribution. Well, the same thing holds true here. Remember why we did that? The log normal distribution was truncated at 0 because prices can't be less than 0. Well, the same thing holds true here. right? What do we know? The variance is sigma squared, so that's a positive number. So we're going to use a test that is reflective of a distribution that is skewed to the right. And there's a picture of this. So this should make perfect sense based on what we talked about in that previous recording. What that means then is that we can't use z and we can't use t because that's not normal. So we use a chi-square test. So here's a great answer to the question. Hey, if we're comparing variances, what's the appropriate test? You use the chi-square test. There we go. It sounds exactly like a stats question, but now you've got LeBron and Steph Curry and dividend-paying stocks to support that purely statistical question. All right, there's the chi-square test statistic. Right above the blue box. So there's the, it's like a funny looking X, right? So squared n minus 1 degrees of freedom. And so there's the S squared. All right, so let's go ahead and work through this. We can have a two-tailed test. There we go. The two-tail, we got some of it over on the left and then some of it over on the right. Notice they are not symmetrical. Of course they're not symmetrical. So let's go ahead and just work through a quick example here. 15-year period, monthly return, standard deviation of 15%. All right, so we've got this financial analyst wants to know whether or not that holds through going forward, right? So the monthly standard deviation between January of 2020 and December of 2021, standard deviation of 4. So we're asking really the same question. 5%. Is that the same as 4%? Well, mathematically, it is a difference, but statistically, we need to figure this out. So let's go ahead and state the null hypothesis. There we go. The variance is equal to 0.0025. It's a two-tailed test, so the alternative is not equal to 0.0025. Since the latter period has the 24 months, we're going to use that in our chi-square distribution. So all we're going to do is say 24 minus 1, put the 4% in the numerator, put the 5% in the denominator. Now make sure you square them, right? And divide by 24 in the numerator. So that gives you 14.72. There's our test statistic. So we need to get out our chi-square distribution. So let's run our finger down, right? There's 23 and minus 1 degrees of freedom. So what are we doing now? It's a 5%, so we're throwing 2.5% in the left tail. So we need to go to 975, right? 1 minus 2.5% is 975, and then we need to go all the way over to the right. So that leaves us with 2.5% in the right tail. So what are those two numbers? Boy, they're too small. I need to fix my glasses here. So what is that? Around 12 and around 38. So what was our chi-square statistic back here? Around 15. So that falls in the middle. So we cannot reject the null hypothesis. So we say something like, even though 5 is different from 4, those standard deviations are not statistically different. And that's our conclusion. Yeah, ladder standard deviation value is close enough to its 15-year value. That's a really cool interpretation, by the way. All right, how about if we say something like, hey, you know what? We have 2 independent random samples. Maybe we have 100 LeBron James in the first 10 years of his career and 100 of LeBron James points in the last 10 years of his career. What we want to do is say, are those 2 standard deviations the same? Well, here is where we're going to do an F test. So this is the only time we use an F test, and this is a ratio. We put 1 standard deviation in the numerator and 1 standard deviation in the denominator. And by the way, the F test, and don't tell your stats professors that I said this, the F test is kind of like an extension of the T tests. In fact, if you do a T test and you do an F test and they're both appropriate, those 2 are going to give you the exact same answer. Now, with F, you got to worry about all that stuff on the right side. So notice the critical region is over on the right side. So let's go ahead and do an example. All right, we're testing whether population variance on a commodity index after the introduction of new trading guidelines. All right, that makes sense. First 320 weeks before, second 320 weeks after. So there's the weekly returns before and after. So it's 18 and 9. The variance is 3, 7 and 2, 9. Are the variance of returns different before or after the guidelines? 5%. All right, so what is our hypothesis? There we go. Standard deviation before, same as standard deviation after. What we're going to do is use the F statistic. So we put the before in the numerator, the after in the denominator. There's our 5%. Now, here's where the learning module says something like, hey, let's not worry about actually calculating those things. Let's just go ahead and give them to you. So left side 803, right side 1246. So there it is. There's the F stat 11864. So the Institute doesn't ask you to look up the F table. It just gives it to you. So I'm guessing that that's what they'll do on the exam. So once again, we're going to fail to reject the null hypothesis because 11864 is in between those two critical values using Excel or getting them from the table. Now, how long have we been going at this? 50 minutes or so. I told you 95% of that was those first two LOSs. So let's just quickly go through this last one here. Contrast and compare parametric and non-parametric tests. All right, so what we've been doing so far in these 50-some minutes is we made an assumption that our underlying distribution was, maybe it was normal, right? The Z and the T, maybe there was a little bit of skewness in there because of we're doing variances, so we did an F test or a chi-square test. So those are parametric tests, but non-parametric tests, they don't really care, and they don't make any assumptions about the underlying distribution. You could have a distribution, like what? Our normal distribution goes like this. But what if you have a distribution that goes like this? Here, I'm just making one up as I'm going along with my hands, right? Well, how about some conditions under when non-parametric testing is appropriate, right? The data do not meet distributional assumptions. So maybe there's skewness, maybe there's kurtosis, maybe there's something else, maybe it's some other kind of a distribution. But the second one is probably a really good exam question when there are outliers. So going back to our dividend paying firms, suppose we collected 100 and, there were 97 of them were between, let's say a minus 2% and a positive 12%. 97% fell within that range. But then you had one that lost 87%. You had one that gained 482%, and then a third one somewhere in there. What do you do when there are outliers that really can impact the assumptions of a normal distribution? Sometimes there are tests done that does not concern a parameter. Maybe we don't want to test for the mean. Maybe we don't want to test for the ratio or the difference between the two standard deviations. Or maybe the data is ordinal, meaning that we don't really know what the data looks like, right? They have natural ordered categories like time, day 1, day 2, day 3, day 4. So those are probably good test questions there, researchers using non-parametric testing. And then the next part of this learning module just asks the question, okay, if you have a non-parametric test, you can't use what we've discussed here. You need to use some other kinds of tests. So I would take a picture of this. Tests concerning a single mean, you're going to use the Wilcox signed rank test. If you're difference between the means, you're going to use the Mann-Whitney test. If you have a paired comparison test, you're going to use that Wilcox sign test, right? So you have this picture and you have those, and this is pretty much what the last LOS covers. So what I want you to do now is I want you to go and take a look at those 20 questions at the end of this learning module. Keep in mind that 19 of them are purely statistical sounding questions. But if you think about the LeBron James, you think about the dividend paying stocks, and then you remember the examples that we did inside of this slide deck, I think you'll be able to answer all of those. The 20th question is the sole question on parametric and non-parametric tests. And if you know this table right here, you can answer that question. So, hey, thanks for watching. Good luck studying. Have a great day.